this is a similar problem to the last one, but because we have the same reaction, it's the same balanced equation, but in this case, it's pretty clear that our reaction is going to have to go backwards, because we're starting with some product, HI, and we are letting it come to equilibrium, so there has to be some reactants that get formed. And again, we have to consider the stoichiometric coefficients. Because there's a 2 stoichiometric coefficient in front of HI, we know that HI is going to disappear twice as fast as the H2 and I2 appear. So when we set up our ice table like such, we know that the change in HI is going to be twice as fast as the change in I2 and H2. And we know that this time we'll be losing HI and gaining H2 and I2. So now let's figure out initial concentrations. This was an empty flask and we just added HI, so we're starting with 0 hydrogen and iodine, and we are given the number of moles of HI, and I'm just saying that I wrote Ki up here, so I'm going to fix that. But anyway, we're given moles of our product, HI. That's not molarity, that's not a concentration yet. But luckily, it's in 1 liter of volume. So it's actually the same number. Because to get molarity, we take moles and divide by volume in liters. And we get 0.05 again. But this time, we can show that it's definitely molarity, a concentration. So now we can put in our equilibrium concentrations. We got XX and 0.05 minus 2x. And here the tricky part is to solve for x so we can figure out our equilibrium concentrations. But we can do it. We can use the equilibrium constant expression and plug in what we know. The equilibrium constant at 600 Kelvin is given as 76. That's our concentration at equilibrium of HI. And we square it. And our hydrogen concentration at equilibrium is X, and also our iodine concentration. So that's our equation we can use to solve for X. I'm going to take this equation and move it to the next page. I'm going to take the square root of both sides. Square root of 76 is 8.718. And the square root of the other side is just that over x. Then I'm going to multiply both sides by x, then add 2x to both sides, then divide both sides by 10.718 to isolate x. And we get 4.67 times 10 to the negative third molar for x, and that is actually the equilibrium concentration of the H2 and I2, because remember, we had x as our equilibrium value for both of those species. So we solved for both of our reactants equilibrium concentration. Now we just got to get the product, HI, equilibrium concentration. And from our ice table, we saw that it was 0.015 minus 2x. 0.05 minus 2x looks like that. And the value you get for that should be 0.0407.
Made with Doodlecast Pro.